Welcome to Short Talks from the Hill, a podcast from the University of Arkansas. I'm Bob Whitby, a science writer for the university. Today we're talking to Celina Suarez, Associate Professor of Geosciences. Suarez joined the university's Department of Geosciences in 2012, and as far as we know is the only University of Arkansas faculty to have a dinosaur named after them, Gemini raptor Suarzarum, which he discovered in 2004 while working on a dig in Utah with her identical twin sister. Her work focuses on using fossil geochemistry to construct ancient environmental conditions. Suarez and her colleagues recently received a grant from the National Science Foundation for research on how climate and tectonic changes influence the evolution, distribution, and extinction of land-based life 90 million years ago in the Late Cretaceous period. She also contributed to the Deep Carbon Observatory, a worldwide group of scientists studying the deep carbon cycle in the Earth. Welcome.
Thank you.
Let's start with your recent NSF grant. What are you studying and why?
So we know a lot about the Late Cretaceous. We know a lot about the diversity of the Late Cretaceous, and the fossil record is really great. We know a lot about the Jurassic period, the late Jurassic period. But this transition between the latest Jurassic to the Late Cretaceous is somewhat of a mystery. Partially that is due to a lack of good chronologic constraint, time constraint of the sedimentary units there. And then part of it is people just really haven't looked in the past at at that specific transition period. So since the diversity in the Late Cretaceous is so extreme and the diversity in the late Jurassic is so extreme, there's been somewhat of a bias of paleontologists and geologists focused on those time periods. And so now what we're trying to do is fill this gap between the latest Jurassic and the Late Cretaceous and what evolutionary changes happened. We know that there was immigration of different fossil groups or animal groups from Asia. We know there was connection between Europe and North America. And we know at a certain point about 98 million years ago that North America was split into two by rising sea level and complete closure of the Western Interior Seaway. So we're interested in looking at how different tectonic and global climate changes occurred in this time period. What's the record of it? How quickly did things change, and how did that affect the evolution of all the different types of dinosaurs that you get into the Late Cretaceous? So
it's a 5-year grant. What are the processes? What do you have to do in those 5 years?
For the University of Arkansas portion, we're mostly focused on generating our time scale. Basically, how old are all of the different sections of rocks that we're going to be looking at from north to south, as well as focusing on the climate record. So my colleague Glenn Sharman here in the department will be focused on looking at detrital zircon geochronology and dating the little bitty zircons that you get. It's just a type of mineral that you get when you have volcanic eruptions. So we'll be dating those minerals, and then myself will be focusing on the isotope record. So if you look at the carbon isotope record over time, the global record shows these peaks and valleys related to changes in CO2 in the atmosphere. And so if we have a somewhat time-constrained record of these carbon isotopes, we can get a better idea of how we can correlate rocks, say, in Texas to rocks in Utah to rocks in Wyoming, so that we're comparing the same time period across the environment.
There's also a component of this looking at mass extinction of certain species. What does that have to do with the geology?
So in the middle part of the Cretaceous, there wasn't exactly major mass extinctions, but there were major fossil turnover or animal turnovers, especially like in the microvertebrate record, but also in the vertebrate record. And so what we're trying to do is compare the climate change that happens. Where do you have big changes in temperature or changes in precipitation patterns? How well does that correlate to fossil turnover of animals?
So the university has these fairly new facilities, the Trail Lab and the Stable Isotope Lab, and they're going to be a big part of this research?
Correct, yes. The Trace Element and Radiogenic Isotope Lab, which is an NSF-funded, includes NSF-funded equipment, is going to be heavily used in this project. All of the uranium lead dates we get from tetratyl zircons will be analyzed on the laser and the ICP-MS that we have in trail. And the Stable Isotope Lab has been continuing to update their mass spec facilities and the equipment that they have. And so we're going to be heavily using the Stable Isotope Lab as well, and probably be analyzing thousands of samples in both lab facilities. So, the instrumentation facilities at the university is going to be rocking pretty hard.
Is that a unique capability that we have?
Yeah, not all universities have state-of-the-art isotope facilities, and so I think we're really lucky to have that. Otherwise, we'd be either sending our students off somewhere else to be analyzing those samples or analyzing the samples elsewhere. And the nice advantage of this is, the money that we got from NSF to do this work is going to be basically flushed through the university, because the money for those samples is going to the Stable Isotope Lab, which goes to upkeep to the stable isotope equipment and improvements of the Stable Isotope Lab, and just increases our standing as a research university.
So you recently published a paper on the role of catastrophic impacts to the Earth and the role that they play in the carbon cycle. Tell us about those findings.
The goal of the Deep Carbon Observatory was to focus on carbon on Earth, where it is, how much is stored in the different reservoirs, and what are the fluxes between those reservoirs. So they were interested in constraining the amount of carbon from the core to the crust and the fluxes between all of those different reservoirs. Over the course of the 10 years, one of the things that they were interested in is understanding these time periods in Earth history where that cycle is out of balance. And since I focus on this a lot in my research, most of my research is focused on these carbon perturbation events in Earth's history, and we basically outlined over the course of this the steady state flux, and then we compared it to catastrophic events. And then it was only logical that we compare it to modern carbon flux into the atmosphere. And so what we have found is that the amount of carbon that is released to the atmosphere is a slight order, like a little bit less than the amount of carbon likely released from the impact of the asteroid that hit in Mexico at the end of the Cretaceous, and also pretty much on par as far as magnitude goes of CO2 released to the atmosphere, the flux per year, to these massive carbon cycle perturbations that occurred during large igneous provinces. So like the big Great Dying, as everybody calls it, the major mass extinction at the end of the Permian, the flux of CO2 that we release to the atmosphere today is similar to the flux of CO2 released through the volcanism in Siberia that basically caused one of the largest mass extinctions in Earth history. So it was a bit sobering.
That doesn't sound like good news.
It doesn't sound good. we're basically on par for these major catastrophic carbon perturbations.
Is it safe to say that the carbon cycle is not in a steady state right now?
On the short term, no. So one of the caveats we have when we look at these deep time carbon perturbations is our geologic record is maybe on the order of about 1,000, tens of thousands of years. What has been happening in the recent past is in like 200 years, for example. So extrapolating a record that is no finer than about 1,000 years to 200 years is a little bit hard. However, when you think about the amount of carbon that has been burned and released to the atmosphere, and most of our carbon that we burn and release to the atmosphere, like fossil fuels, are ironically from the Cretaceous. Probably because there was lots of carbon emitted into the atmosphere in the Cretaceous, and this is that record that has been buried, as well as the Paleozoic about 250, 300 million years ago, and that's mostly our record of coal. We've burned almost all of that, which has taken millions of years to form, in less than 200 years. So when you just think about the actual fluxes of carbon, I would say we're probably in a non-steady state at this point.
Sounds like
the
it.
The consequences of that non-steady state can be debated. Natural scrubbing of CO2 from the atmosphere occurs from weathering of rocks, and that happens over the course of about tens tens of thousands of years is the rate of CO2 removal from the atmosphere. So, in 10,000 years, we may be back into a steady state.
It's going to be a while then.
Yeah.
Music for Short Talks from the Hill was written and performed by local musician Ben Harris. For more information and additional podcasts, visit researchfrontiers.ur.edu, the home of research news at the University of Arkansas.